So today's lesson, I'm going to actually start with something a little bit weird. The assignment that I gave that I believe is due today, quite a few students were struggling with question number 4, which had to do with finding the point of intersection of 3 different equations, and from that calculating the perimeter of the shape that was formed. Now, finding the point of intersection is grade 10 curriculum material. So it's important that you don't forget everything you've learned from previous years. Now, you're allowed to forget it temporarily, but you should very quickly be able to either look back at notes from the year before, or look at some videos online and quickly pick it up again, which is what I was kind of expecting you to do. But because so many people were struggling with it, I thought I'd maybe start today with a brief little recap of what a linear system of equations looks like. So I'm glad somebody took a look at their binder from last year. I hear so often about students burning their binders from year to year, but it's really important to keep those things in the closer you get to university, like your grade 12 binders, you should be storing those somewhere very important to you. Now, as we go towards digital, I'm just thinking you could always, I guess, potentially scan them into something, but it might just be easier. I actually took all my pages out of my binders and put them in filing folders. I thought it took up a lot less room in my organizational structure of my room. But anyway, I am going to do a quick little recap of solving a linear system. We're going to talk about solving a linear system by substitution. I'm going to talk about solving a linear system by elimination, and then I'm going to show you, I'm hoping, something new for most of you, which is solving using a matrix. So let's get to it. We're going to start by a substitution example. So I hope I'm not getting the hiccups here. So let's say we had 2 lines drawn on a Cartesian plane. Okay. And so forget about these 2 equations here for a second. This is an example of the elimination method. I actually want to start with the substitution method instead. So let's pretend that I had given you the equations for these 2 lines as y is equal to 2x plus 3 and y is equal to 4x plus 1, which is usually where grade 10 curriculum starts, somewhere with linear systems. Okay. Now, the idea here is because these 2 lines have different slopes, that they have to cross somewhere. All right, there's going to be a point of intersection. You can actually see the point of intersection right here. And I just realized my green line is a little bit low to have that structure, so I'm just going to move it to here to make it look a little bit more realistic with the equations. So what do I mean by that? Well, look at the y-intercept value. So the y-intercept value of one of the equations is 1. That's 1. The other one is 3. That's 3. So I just want to make it look a little bit more realistic. How do you solve a linear system when both equations are in y equals mx plus b format? Well, there are 2 different ways of solving a linear system. There's substitution and there's elimination. And today I'm going to show you a 3rd one called matrices. The substitution method basically says that because both lines cross at the same point, that means the green and the red line both have the same y value at that point. Now, they also have the same x value, but we usually isolate y. So it's more important for us to talk about y because the y's are isolated. Okay? So they have the same y value. And if they have the same y value, that means the y value from the second equation can be substituted into the y value of the first equation, because they're the same, right? So what you end up with is 4x plus 1 equals to 2x plus 3. And then with a quick switcheroo of the x values and the constant values, we end up with 2x is equal to 2x is equal to 2 and x is equal to 1. So I now know that the point where those 2 lines cross is at x equals 1. And if I want to find the y value, I just substitute x equals 1 back up into there, right? So if x is equal to 1, I'd have 2 times 1 plus 3, which would be 5. And I now know that this height is 5. So I know that the point of intersection is 1, 5. And for that question in your assignment, you had 3 equations. You were technically supposed to do it with all 3. Now, as of this moment, Nobody has figured out that there are tricks that you can use with question number 4 to make it much, much simpler for yourselves. And I'm not going to give those tricks away yet because some people haven't handed in the assignment yet. But there would have been a way that you could have easily found one point of intersection and known all of the other ones just from that one point. So, well, sorry, I'm lying. From the equations, you knew a point. From the solving the linear system, you would have known a second point. And just knowing those 2 points, you would have known all the information you needed to solve the perimeter. But maybe I'll get back to that another time. Let's look at this elimination method scenario. Now, why is this an elimination method scenario here? Because the equations are not written in y equals mx plus b format. Now, we could isolate them to be y equals mx plus b. But when you isolate the second equation, because there's a coefficient in front of y, you're going to be dividing everything by 3, which means you're going to end up with some pretty ugly fractions sometimes, okay? So there's a better way. Now, the elimination method says if there was a way of adding down one of the columns, so either the x column or the y column, if we could add down and have the x's eliminate each other, we'd have gotten rid of one of the variables and then we could isolate the other one. Well, in this case, we can't add down, but there's another rule. Yes, now I want to add down. I don't want to subtract down. I know there's a way of doing both, but it's always better to add rather than subtract. So if I want to add down to make the equation cancel the x values, if I call this equation 1 and I call this equation 2, I'm going to multiply equation 2 times negative 2. Okay? And that's going to change equation 2. Now, equation 1 stays the same, so we just rewrite it. Equation 2 is going to be multiplied, like I said, by negative 2. So this is going to become negative 4. 3 times negative 2 is going to be negative 6. And 6 times negative 2 is negative 12. Now let me fill in the rest. And as I mentioned before, folks, this is a Monday morning, or now it's afternoon, sorry. It's a Monday afternoon. I made a lot of silly mistakes in the previous lesson, so please watch me carefully. I'm talking a lot and not paying attention to what I'm doing, so make sure if I make a mistake to let me know in chat. So I multiplied every coefficient here by negative 2, which is the same equation. Proportionally, it's the same equation. If I divided it back by negative 2, I'd get the exact same equation back. But what's nice about this one is I can add down the columns now. If I add 4x minus 4x, that gives me 0, which we usually don't write. Negative y minus 6y is negative 7y. 10, I know it's adding. Negative 6 plus negative 1 plus negative 6. 10 plus negative 12 is 10 minus 12, which is negative 2. And now I can isolate y to be negative 2 over negative 7, which is just 2 over 7. And then I'd have to resubstitute that 2 over 7 back into one of the original equations to find the x value. Then I'd know the x value as well, and I'd know the point of intersection. So what is the matrix method? The matrix method is based on elimination. And it's actually called Gaussian elimination or Gauss-Jordan elimination, depending on the style of elimination you're using. So what is a matrix? Well, a matrix is just another way of writing the two equations in a row by column format. Okay, rows by columns come back a lot in my teaching and frankly in my learning throughout the years. This style of organizing information is very, very common in mathematics. Okay, and here's what we do. Instead of writing out the entire equation 4x minus y equals 10, let's just look at the coefficients. The coefficient for x is 4, the coefficient for y is negative 1, and the answer is 10. For the second equation, it's 2, 3, and 6. Coefficient for x is 2, coefficient for y is 3, coefficient for or not the coefficient, but the constant term is 6. Now this line here just basically means the equal sign, and this would be the x column, and this would be the y column. And we're basically going to do the exact same thing as what we did for elimination, but we're going to use the structure of our matrix to keep everything organized. Now, you're probably going to see that this example I'm about to show you does not look more efficient than what we just did, all right? And maybe it isn't for a linear system with only 2 variables. But I can guarantee you that when you get into 3 dimensions and you're working with equations that look like this, oops, okay, and you have 3 of those equations, and you have to solve for x, y, and z for the point of intersection, there is nothing better than using a matrix to solve that. All right. Now, the other reason it's not going to look very efficient is I'm going to show this to you step by excruciating step. And there are shortcuts to these steps, but I don't want to show you shortcuts today. It's potentially the first time you're seeing this. Okay. And I'm doing this mainly for fun before we get into today's real lesson, because it is fun for me and it is something that you're going to need. My daughter just came down here and spoke to me. She's in second year university. They use matrices all the time. Okay. And it's stronger in probability statistics, but you will see it in physics. You will see it in mathematics and calculus, for instance. It is something that's used everywhere. So the sooner you get your brain used to this layout, it will not be a shock as much the next time you see it. Okay. All right. So here's the idea behind solving the system of equations with a matrix. We want a 0 in this position. And if we're really good, we also want a 0 in this position. But the only way you can make zeros appear is by combining the two equations together, basically the same way we did up above. All right. So if I call this equation 1 and I call this equation 2, the first thing we're going to do is multiply equation 2 by 2. By negative 2, sorry. So we're going to multiply equation 2 by negative 2, just like we did above. That's going to change the second equation. Okay, so their first equation stays the same. Our second equation is going to become negative 4, negative 6, and negative 12. Okay, and we're going to call that new equation equation 3 because we changed it. It's no longer equation 2, it's now equation 3. And here's where the quote-unquote magic of a matrix starts to happen. When you combine two equations, you replace the row by the answers of that combination. So we want to combine equation 1 plus equation 3, and we're going to put the answer in this row. Okay, so once again, equation 1 doesn't change. But when I add the equation 1, which is 4, plus equation 3, which is negative 4, I put the answer in this position. That becomes 0. So I'm basically just adding down each column here. Negative 1 plus negative 6 is negative 7. 10 plus negative 12 is negative 2. Now you might be able to see that this negative 7 and this negative 2 are the exact same numbers we got, whoops, sorry about that, the exact same numbers we got here and here. Okay, but we're not done. Like I said, if you're really good, you're going to want to have a 0 in this position as well. So how do I get a 0 in that position? Well, I have to combine upwards towards this negative 1 with this bottom equation. But right now, that's not going to give me 0. If I add upwards, it doesn't give me 0. So what number would I really like to have right here? I wonder if anybody can tell me in chat. That's right. I want a 7 right there, because 7 plus negative 7 would give me 0. So if I can transform that into a 7, I'll be able to add up and get 0. So what are we going to do? Now I'm going to do this off to the side instead of going down a row on my page here, just so that you can see what's going on. So I'm going to multiply this row times 7. Now that is row 1 still, by the way. So we're going to do 1 times 7. That's going to give me 28. Oh, wait a second. No, I want it to be negative 7. I need to multiply by negative 7. First mistake of the day. Because I want it to be a positive 7 in this position. Okay, so 4 times negative 7 is negative 28. Negative 1 times negative 7 is positive 7. And then 10 times negative 7 is negative 70. Right? I don't think I made any mistakes there. And then my second row stays the same. So 0, -7, -2. Now I have to go down a little bit. So now I'm going to add upwards. All right. So if you remember, you know what? I'm just going to forget about let's just add upwards. It'll make it easier than writing down all of the indexes on the outside there. So adding upwards, we get 0 plus -28, and we replace the -28 by that number, which is still -28. -7 plus 7 is 0, so we replace that number by 0. And -2 plus -70 is -72. Okay. This is what's called a reduced matrix used to solve linear systems, right? Why is it necessary to get the zeros in those two positions? Well, I want to remind you that this column is the x column and this column is the y column. Remember that the -28 is just the coefficient of x. The line here is just an equal sign. Okay, so this line just represents an equal sign. So I can take that first line now and write -28 times x equals -72. And I can write the second line as -7y equals -2. And now I can isolate for both x and y. X is equal to 72 over 28. And y is equal to 2 over 7 if we reduce it. Now this one can be reduced as well, the 78 over 28, but I'm not going to, the 72, sorry, that's a 72. 72 over 28 can reduce a little bit. All right, but I've now found my point of intersection. So I know some of you are going to say, but sir, look at all the writing you did for those matrices and look at the writing you did for the elimination method. Clearly the elimination method is much, much faster. Well, like I said, there's a lot of shortcuts we can take. For instance, every line here that I was multiplying just by a number, I could have said multiply by the number and add down at the same time. So we could have skipped that matrix and gone directly to this one. And we could have skipped this matrix and from there gone directly to that one. So yeah, it might seem like it's a little bit more writing, and you might be right that it is for this particular example. And remember that we didn't find the x value up there yet either. But I'm guaranteeing you that if you're doing a 3x3 matrix, and in one of my classes, I believe it was an algebra class in university, second year, we did a 10x10 matrix this way, by hand. And then we had to go to a computer room and program it. Okay? So imagine having 10 variables by 10 equations and trying to get, and in a case like that, you'd have this huge matrix and you're trying to get zeros down this corner and zeros up this corner. And I didn't do my augmented matrix there, but anyway. And then you'd have all of your answers for each one of those variables. Okay? It was very long, but the power of that technique, to imagine doing that with equations, it would have just been not doable. Okay? So that was my very, very quick introduction to matrices for solving a linear system. When I teach my grade 10 class, this is actually the way I show them how to do it, because I want them to get used to it as fast as possible. But if you've never seen it before, at least now you've seen what they look like. I know I went through that really fast. You're never going to have to repeat that in this class. But if you do take data management in grade 12, guaranteed you're using matrices. I'm not sure about your IB classes. Like for physics, we often use matrices for vectors. I don't know how far they go in high school, but you will be doing it in university if you take university physics. So, all right, moving on to the actual lesson for today. So today we're going to be looking at rational functions. Now, rational functions, what that means is rational means fractions, and specifically what happens if there's x's in the denominators. Now, I'm going to start with a quick little warm-up here of how to multiply polynomials. And you've already seen some of this with me. I like to do it in a very specific way. I'd kind of like to reintroduce that way. And this way you'll have a video showing how to do it if you ever need to go back to it. Some of you are going to like what I'm about to do. Some of you already have your own methods. I am going to try to convince you that my way is better. But if you prefer your own methods, that's fine. All right. But and I'm going to warm you up with this little easy one here. What happens if you can't use FOIL? Now remember, FOIL is just an acronym to help us do binom times binom. But if you don't have a binom times a binom, for instance, we have a binom times a trinome here. How do you multiply those two together? Well, you can't use FOIL. You use multiple distributivity. You're going to distribute the x through all three, and you're going to distribute the 3 to all three. And it shouldn't take you much calculations to figure out that that means we're going to have 6 different terms that we're adding there. Well, the way I like to do this is the idea of row times column. Now, I didn't get this from matrices. I technically got this from algebra tiles. But I find that if I write it this way, right away I can tell exactly how many terms I'm going to end up. And there's another nice thing that happens as well. So let's multiply row times column. And all I did is take the x plus 3 and write it down the edge here. And the 3x plus 4x plus 6 and write it along the top edge here. And that formed my row times column structure. So we're going to do x times 3x squared, which is 3x cubed. X times negative 4x, which is negative 4x squared. X times 6, which is 6x. And then 3 times 3x squared, which is 9x squared. 3 times negative 4x, which is negative 12x. And 3 times 6, which is 18. Now something very interesting happens. Sorry, I just need to get a little bit of a drink here. Something really interesting happens here in that all of the diagonals represent your like terms. And if there's anything I like about this method, it's this right here. Because if you can imagine, if you had distributed the x's all the way through and the 3's all the way through, your like terms wouldn't be side by side. You'd have to go hunting through all of those 6 terms to find which ones are your like terms and group them together. Now this will only work if all of your terms in the polynomial are present. And what I mean by that, and we've already talked about this when we were doing long division, when you have a quadratic, you have an x to the power of 2, an x to the power of 1, and an x to the power of 0 hiding in the equation. If one of the terms is missing, you won't end up with this diagonal structure that I'm talking about here, okay? But as long as all of the terms are present, this will always work. And it's really easy now to group up your like terms. So our final answer is going to be 3x to the power of 3. We've got 9 minus 4x squared, which is plus 5x squared. Minus 12x plus 6x, which is minus 6x, plus 18. Okay, and I'd be willing to say, well, sir, I'd prefer to do it distributivity. You know, if you want to do it all in one line, you prefer to do it that way, fine. But what about this one? Now, we'd end up with 9 terms all lined up with our like terms not being next to each other. But if you set it up like this, I can clearly see how many terms I'm going to end up with. And all my like terms are going to be along those diagonals again. So let's fill this in. And this is where I made some silly mistakes earlier, so please watch me carefully here. So 4x squared times 2x squared. Let me use a different color for that. So that's going to be 8x to the power of 4. And then 4x squared times negative 3x is going to be negative 12x cubed. And 4x squared times negative 4 is going to be negative 16x squared. Negative 5x times 2x squared is negative 10x to the 3. Negative 5x times negative 3x is positive 15x squared. Negative 5x times negative 4, positive 20x. And then 3 times 2x squared. Yeah, well, you're not explaining it to anybody. Somebody just said the other way is faster. 3 times negative 3 is negative 9x. 3 times negative 4 negative 12. And then if we look down the diagonals, there are like terms, there are like terms, there are like terms. I'd be willing to have a race with you. And now we just group them up. So we've got our 8x to the power of 4, our negative 10x cubed minus 12x cubed is minus 22x cubed. Now, basically, this is 6 minus 1, because 15 minus 16 is negative 1. So 6 minus 1 is 5x squared. And then plus 11x minus 12. Okay. Yeah, you might be right. You might be right that the other way is a little faster. I agree that having to write out the structure is going to take a little bit of time. But I've gotten to a point where I like this much more, just simply because I don't have to hunt down my like terms. And again, this is a 3 by 3. Imagine doing a 5 by 5 or a 6 by 6. Like, your like terms are going to be spread out so far. And this is just with two variables. If you had like ABs and A squares, B cubes, and all this stuff, it can get very, very complicated. So I'm thinking about those more complicated ones. You can use whatever way you're more comfortable with. I like this way because I can see exactly where all my like terms are and very easily group them up without having to hunt them down. So it's up to you. I just wanted to show that to you one more time. And that's just our warm-up for today. Stuff you already know how to do. Let's move on to the new stuff. So as I was saying, rational expressions mean fractions that are going to have x terms at the top and x terms at the bottom. X terms at the bottom are supposed to be new this year. How do we deal with x's that are at the bottom of fractions when we're dealing with expressions? Well, one of the first things I want to talk about is restrictions. The problem with x values at the bottom is that if you're dividing by a value that doesn't make any sense, you have to restrict that value. Now, what do I mean by that? Well, there are values of x that can break the answer. Because if you end up with a 1 over 0, you're not ever supposed to have that. So if you have x's at the bottom of your equation, you could potentially end up with a scenario where you'd have a 1 over 0 or a something over 0 scenario. Now remember, in calculus, and I've talked about calculus a little bit, we are going to do limits when you take calculus, you're going to be doing limits as x approaches 0, but you're never technically getting to 0. So 1 over 0 or anything over 0 is still considered undefined, and you're not supposed to do it. So let's look at an example and explain what I'm talking about with an example. Is there a restriction to 1 over x minus 2? Well, what would make this equal to 0? And the answer's already been given. Basically, this is like finding your roots in quadratics, but instead of saying they're equal to 0 to find your roots, you're saying they're not equal to 0 to find your restrictions. And it's only the denominators of the fractions right now. We'll talk about that later. So what you're doing is you're setting x minus 2 can't be equal to 0, therefore x can't be equal to 2. Okay, so I'm writing it out the long way here. I'm sure everybody can see that if I put a 2 in for x, 2 minus 2 would give me 0. And the way you write the restriction is x can't be equal to 2, right next to the expression with a comma separating them. That's the format. And it's really as easy as that. Now, what about this one? What would be my two restrictions? Well, if we look at the first one, and I am going to do this the long way right now, okay? For this one here, you'd write 3x plus 4 can't equal to 0, and then isolate x. Well, if you isolate x, you're going to end up with a negative 4 on the other side. and then you're going to isolate by dividing by 3. But we talked about this when we were finding roots way back when. If you have a coefficient in front of x and you have a constant number adding or subtracting, your 0, if this was a quadratic, would always be the opposite sign of your constant value divided by the coefficient. So you shouldn't have to write all these steps out. If you have to, go ahead, but you shouldn't have to. You should technically be able to do that in your head now and just tell me that the restriction would be -4/3. This restriction is easy. What x value would make that denominator equal to 0? And then you usually list them in numerical order. So x can't be equal to -5 or -4/3. And chat is answering as well. Okay. Let's throw in a little bit of a more complicated one here now. What about this guy? Now, before I talk about this one, I want to go back to this example for just a second. X, the very first one where we said x can't be equal to 2. Why do we have to state restrictions? Well, the reason is that if we were to graph this relationship, at x equals 2, something is happening, which means the graph doesn't exist at that point. And if you remember way back to when we were doing our domains and ranges, there were graphs that had holes in them, and there were also graphs that had asymptotes in them. This is basically what we're saying here, is we're saying where are the holes on the graph, or where are the asymptotes on the graph. Now, let's scan your memory here. This is a 1/x graph. Do you remember what a 1/x graph looks like? Do you remember your 7 deadly curves? A 1/x graph sorry, it's really hard to draw curves here. That's not a very nice curve. Let's try that again. Looks like this, and there are asymptotes along the y-axis and along the x-axis. Chat, which way did the 1/x graph move? When you have an x minus 2, where the -2 is right next to the x, it does the opposite, and chat is correct. This is moving right by 2. So the whole graph, including, well, the horizontal asymptote doesn't move because it's infinite. The whole graph is moving to the right by 2. That's what this restriction is talking about. It's talking about that domain that has now an asymptote at x equals 2, which means the graph doesn't exist at x equals 2. Okay? Now, for this example, what does that graph look like? I have no idea. But I do know at x equals -5 and at x equals -4/3, something weird is happening. Okay? Now, what about this guy? Well, for this one, let's do it the same way we would do in the other ones. Let's look at the denominators and call up our restrictions. Now, without taking too much time here, you should be able to tell me what this restriction is. And you should also be able to really quickly tell me what this one is now. If we follow the pattern that I told you earlier, pretend you were finding a 0. You'd go +3 divided by 2. Okay? So we're going to leave it as a fraction, though. The further we move on, the less I'm going to want to see decimals in our answers. Okay? Unless we're working with real-world problems with money values or whatever, we're going to keep it as a fraction. But and this is why this section I consider to be actually probably the hardest section of the year. And it isn't because of the math. It's because of fractions. So many students struggle with fractions and all the rules involved with fractions that when we start mixing in algebra of x's along with the fraction rules, students really start to panic if they're not comfortable with their fraction rules. What do we do when we divide by a fraction? What is the rule? Correct. We have to multiply by the reciprocal of the other fraction. But as soon as we do that, look at what happens here. The x minus 7 that was at the top now becomes a denominator. It also causes a restriction. So why the heck would that happen? Well, you have to assume that the mathematician that wrote this equation wrote it for a very specific reason. Wrote it to say there is something going on at 3/2, but there's also something going on at x equals 7. So this is going to cause us to have... Can you see that on the screen, folks? Or is... You know what? I'm just going to move everything over a little bit. I know that my screen gets cut off. Whoa. When I get close to the edge. Still visible? Okay, perfect. Yeah, so the mathematician that created this expression up here, the original division one, for some reason wrote it this way to tell us there is a restriction at 3/2, and then when you do the flip, there's also a restriction at 7. Okay? But if you can get past that, like that's really one of the more difficult examples right there. So the idea of restrictions shouldn't be difficult, I hope, with the idea that you can't divide by 0, so therefore certain x values can't work. And then just be careful with what they give you originally. Are there any questions about restrictions or how we find them before we move on? Okay, seeing no questions in chat, we're going to finish with this example here, which actually technically doesn't finish the whole lesson, but because I added on the matrix stuff at the beginning, it kind of slowed me down a bit, but that's okay. I don't mind doing that because I felt it was important enough to do. This is going to be your first example into what we're going to be asking you to do in this unit. Can you simplify this? Now, the very first thing you're going to do is you're going to write your restrictions. What is the only restriction to this expression? So I was very worried that somebody was going to say x can't be equal to -6. But you are correct. X can't be equal to 0 is your restriction. Okay? So that was weird. Okay. Now that we've got the restriction done, I'm going to ask chat again. What is the mathematical method that we need to use to divide these things? I don't know why it was censored. I have no idea. I do have the censoring on high, yeah. I'm not sure what happened there. Yeah, I allowed it to go through. I have no idea why it was censored. Yeah, it probably had too many X's in it or something. Okay, yes. So x can't be equal to 0. So let me ask the question again. I'm asking you for a word, okay? A word. What is the mathematical technique we use to divide these two? I'll give you a hint. We recently used the exact same technique with radicals and complex numbers. And nope. I want to divide these two. I've got to do something to be able to divide them. And I know some of you are thinking ahead and just doing the final answer. But there's a step that you have to do. I'll give you another hint. Everything at the top is adding or subtracting, adding in this case, which is evil. You can't divide when things are adding and subtracting. Aha! What you actually have to do is factor. You have to factor the top before you can cancel it out. Okay? And some of you can do that on the fly, and that's fine. But I want you to understand the math that's happening. We're changing an addition and subtraction scenario, addition in this case, to a multiplication scenario by factoring the numerator. So what can we pull out of all three of those terms as a factor? They actually all contain a 6x. And only once that happens can we now cross off the 6x with the 6x. Okay? For those of you that are a little stronger, you might have seen that we could simplify 6x at the bottom with all three terms at the top. But I cannot tell you how many students have just done this on me in the past that have driven me crazy. Okay? You're not allowed to just divide out from the 24. It's all three terms at the top that are being affected by the 6x. So if you factor it first, you're going to see that happen. And our final answer will be 4x squared plus x plus 2. Now I want you to understand that that is a parabola. It didn't start off as a parabola. But if I graph that top equation, the original expression, it would give me a parabolic shape. But what would happen at x equals 0? Sub in x equals 0 here. That gives 2, right? But x can't be equal to 0. So what happens at 2? At 2, there's an open circle. Now, I haven't checked what this parabola looks like, but I'm guessing it's a parabola that looks like this. On my first glance, that does not look factorable, so I'm assuming it has complex roots, which means it doesn't cross through the x-axis. It is a smile parabola, which is all stuff you should know. Maybe not the complex root thing. You might not have been done. I did that really quick. I did 4 times 2 is 8. Two numbers that multiply to 8 and add to 1. Okay, I'm not sure if there's complex roots or not. I'm assuming there might be, but I'd have to actually check with the discriminant. Which, yes, there'd definitely be complex roots. But it's a smile shape because the leading coefficient is positive. Remember the stuff about leading coefficient and odd and even powers or degrees? Okay, all that stuff here is helping me realize that this graph is a parabola that at a value of 2 has an open circle on it. And this expression up here is designed to tell you that there's an open circle there for whatever reason. When you simplify it, you can see the parabola, but you need to know what that restriction is because there's an open circle on that graph. I'd be curious as to what Desmos would do with something like that. So we're going to stop the lesson here for today. So I'm going to say bye for the recording.